All right, in this tutorial, we're going to go over the big ideas, Algebra 2, Section 4.2, adding, subtracting, and multiplying polynomials. So we're going to be able to add and subtract multiple polynomials, multiply polynomials, and then using Pascal's Triangle to help expand binomials with degrees that are higher than 2. So first, adding and subtracting. There are a couple different ways that you can organize your polynomials. There's both vertical and horizontal format. They're going to give you the same answer. It's just a different way of making sure that you're combining like terms together. So first, in your vertical format, when you are writing your two polynomials on top of each other, the one thing that may help you organize your terms together is to make sure that they are lined up vertically in common terms. So notice how your x thirds are right on top of each other, x squareds, x's, and numbers. So if you don't have an x, or if you don't have a certain term, leave a space for it, and then that's just going to go right down there at the bottom. So then you add straight down like you normally would. 3 plus 1 is 4. 2 plus negative 10 is negative 8. Then negative 1x, and then negative 7 plus 8. Horizontal is the exact same thing. So you can just put parentheses around the first one and the second one. And then again, just making sure that when you are combining them together, that you put the like terms together next to each other. So your 3y squared and your negative 5y squared go together, negative 2y and your y go together, so on and so forth. So whichever way you want to organize them is okay, as long as you're combining like terms. So subtracting, the only thing that is different when it comes to subtracting is to make sure that you are thinking about distributing that negative within every single term. So you have a positive 8 and you are subtracting that negative 2 underneath with the x third. You have your negative 3 and you are subtracting that positive 6. So you're always going to think of it as adding the opposite instead of subtracting. So you have your 8, negative 2, negative 6, positive 1, negative 1. So that is changing every single term on the second polynomial. And then you can add it just like the normal we did last time. When they're horizontal, again, think of it as distributing that negative into every single term over on the right-hand side. So instead of a positive 3z squared, you have a negative 3z squared. Instead of a positive z, it changes to negative, and then the double negative to get the positive 4 right here. Combine like terms like you normally would, and there's your new polynomial. Multiplying. So multiplying down in vertical format is very similar to how you would multiply a 3-digit number to a 2-digit number. So you have to make sure that you take all 3 of these terms times your negative 3, and then all 3 of these terms times your positive x. So the first 3 terms in your first polynomial times negative 3 gives you right here. So negative x squared times negative 3 is a positive 3x squared. 2x times negative 3 is negative 6x. 4 times negative 3 is negative 12. Then you're going to shift everything over and then take all of 3 of these terms times the positive x, and this is the polynomial that you get. Whenever you get each individual term, make sure that in vertical format that you're aligning everything up as like terms. That way you can combine them together to get your new polynomial. In horizontal format, you can just think of it as FOIL whenever we did with binomials, but the one thing you have to make sure is taking each individual term of your binomial times everything. So you take your y times everything here, and then take your 5 times everything here. So it's almost like a double distribute with every single term inside there. So you're distributing once with your y plus 5s to each term, and then you distribute each term into your y plus 5 as you are combining them back together. Once you've multiplied, combine your like terms with the same letter and exponent to get your new polynomial. Again, all of your answers need to be written in standard form, so highest exponent first, then the next lowest, and the next lowest, and the next lowest. So multiplying them in horizontal format, all 3 of these together, really what you just want to make sure is that you're multiplying 2 at a time. So notice here they're taking x minus 1 and x plus 4, foiling those first, and then you can take this x plus 5, double distribute it into everything that's happening in your first polynomial term from there. So you cannot really multiply all 3 of those together at the same time. It's easiest if you just pick 2 to distribute first for your foiling, and then you got your distribute with everything there at the end. All right, so proving that the polynomial identity for the cube of a binomial representation is a sum. So you have your 8 plus b to the 3rd power will give you this expression depending on what your a and your b terms are. That's a given fact with your anything raised to the 3rd power. So all you have to do is rewrite this out into your 3 different expressions. And the way that you did similar in the very last example right here is you have your double distribute with your 3 different binomials. It's the exact same thing. So you would take your a plus b and a plus b, multiply those together in your FOIL to get this expression. Then you would just double distribute with your a and then with your b. Combine all of those together. Notice that you have 1a squared b, 2a squared b, that gives you your 3. And then same thing over here, ab squared and 2 more ab squareds to get 3. So we're using now the cube of the binomial in part A to plug in for 11 to the 3rd power to make sure that you get a different expression when you're adding those together. A different way you could get is 10 plus 1. So 10 could be your A and 1 could be your B. So you plug in those right there, and you can just use this final line that we got in part A to do 10 squared, then 3, or 10 to the 3rd power, sorry, and 3 times 10 squared times 1, then 3 times 10 times 1 squared, and then 1 cubed. Multiplying those out and then following up your PEMDAS with your adds and subtracts to get 1,331. All right, so finding each product of a couple special multiplication problems. Difference of perfect squares is going to be your first one. So notice how they are the exact same term, but the only thing is changing. 1 is plus, 1 is minus. So all you need to do is square the first term, square the second one, and subtract. Again, that is called difference of perfect squares. So then when you square those, you get 16n squared minus 25. Remember to square each term individually inside your parentheses, 4 squared, n squared. Part B, if you have the exact same thing, 9y minus 2 squared, you're going to take the first and your last term as each one squared, and then you're going to subtract 2 times each one of your middle terms. So this is another property that you'll need to be familiar with to make this a little bit easier. You can still write these out separately of 9y minus 2, 9y minus 2, and then FOIL like normal. This is just getting used to some of the shortcuts of your squares. Again, following your exponent rules, 9 squared is 81, y squared is y squared. Multiplying all the coefficients, and then 2 squared is 4. Whenever you have a power to the 3, again, similar to that last slide, this is what your property is going to be. So you take the first term cubed, then 3 times squared raised to the power of 1, 3 times raised to the power of 1 squared, and then the last term cubed, simplifying down from there. All right, last thing is looking at Pascal's triangle. So Pascal's triangle is something that will help you expand binomials that have a larger than 3 exponent, or larger than 2 exponents, sorry. So each row is going to tell you what the coefficients of each term is going to be. So notice how this is x minus 2 to the 5th. Well, if you go to what a Pascal's triangle is going to look like, you may have to Google that. So your coefficients of the 5 terms are 1, 5, 10, 10, 5, and 1 in that order. And then you just take your first term raised to the highest exponent, and then you decrease from there. So notice how your x's, you have x to the 5, x to the 4, x to the 3, x squared, x to the 1, and then x to the 0 doesn't exist. Then on the other hand, you take your second term, you start with that term raised to the 0 and then increase from there. So -2 to the 0 power, -2 to the first power, -2 squared, -2 to the 3rd, -2 to the 4th, and -2 to the 5th. Then you just multiply the coefficients up front, You should not need to combine anything at the end because you will have unique exponents for all of your terms. You'll have a 5, 4, 3, 2, 1, 0 in that order. Looking at part B, so your exponent is to the 3, so we're going to look at the third row of Pascal's triangle, and that is 1, 3, 3, 1. So again, taking each individual term, multiplying them by our blue coefficients that we got from Pascal's triangle. Then we have our first term to the third power, then our 3y squared, 3y to the 1, and then the last one is 3y to the 0. Conversely, looking at the second term, 1 to the 0 power, 1 to the first power, 1 squared, and 1 to the third. Following your exponents and your multiplication down there at the end, you're going to get all unique number of exponents. So that is your final polynomial expression.